Okay. So for the rest of the slides, they have not as well been updated or put into the new format for all the slides because it's a huge amount of work to convert everything from the way they were done here, which is in R, to Python. But that will probably happen eventually. But all the links are still on the site. And so if you're interested in going through them, they're there. Also, the recordings will be available. So this is sort of where we left off with the feature vector. This is a slightly different example that we'll show here, where you have sort of a very, if you're trying to do this ring, for example, and you want to segment this ring out. So the first example we had was with the text, but now if you're trying to do the ring and you do a threshold, you end up with this problem that you get the middle area and the edge areas as well, because they have the same intensity as the ring does. And so how can you sort of get around that problem? And that's where you can start adding sort of new features. And so we had the edge feature before with the text image. With this image, what we can add is sort of a distance from the center feature. And this is also the kind of feature that often comes up in medical imaging or even Connect. And so for those of you, does anyone have Xbox here? Does anyone know what a Connect is? Okay, well, it's basically this depth camera on the top of the Xbox that lets you sort of interact physically when you're playing a game. I'm not aware of what games use this, but apparently it's important to know where your left arm, your right arm, your legs, your hands, and you go in different postures and it recognizes it. And clearly, if you were to try to segment based on skin color, you wouldn't really be able to tell the difference between your left hand and your right hand. But when you start to add position or distance from center, it makes it easier to begin to perform thresholds which group things together as you would want them to be grouped together. And so this is obviously a very simple feature for that. But here, if you just include sort of the distance from the center, we can now see that if you have sort of an intensity on one axis and the distance on the other, that there's sort of a group here which corresponds to our ring, which is now very easy to separate from these points and these points, which are the points we were including before. And so we can end up by just taking a threshold in 2 dimensions or along both of these depth axes, so if the distance is between 5 and 10 and the intensity is between 0.3 and 1, that we end up with exactly the ring without including these points because we're able to add that additional feature into what we're doing so that you can make a clear distinction between these 2 phases. Again, you can apply all of this with sort of the ground truth, the ROC curves. You can make these true positive, false positive, whatever, recall precision, and end up with the curve there. True positive rate, false positive rate. So again, this is the standard representation that we'll use because this is easier to make. And this is what KNIME and scikit-learn as a default show, but both of those representations are really the same thing. Again, you can add different features based on sort of the filters we've discussed before, and so you can include not just the intensity, but Sobel and Gaussian filters. Sobel would be sort of more of the edges. So if you were interested in objects that were sort of edge-like, adding Sobel as a feature would be useful. And Gaussian then smooths everything out. And so if you're interested in objects that are very similar to their neighbors or very different from their neighbors, Gaussian or filters can do that step. You can also do entropy or a number of other approaches. And so if we analyze the sort of the feature value for each one of these groups, we can see that they give us slightly different pieces of information. So these distributions don't all look the same. We see that there is some split between the values there, which makes it easier for us to then use that as a cutoff and incorporate multiple of them to do a better job of sort of segmenting the points. And so we see here sort of the pink points are part of the ring and the blue points are not. And if we just picked any one feature there, like intensity and Gaussian, they don't give us that much information. But if we include Sobel as well, we start to see sort of a region where it's very distinct from the other groups. So in terms of applying this technique to other kinds of data sets, there's a more sort of general way to deal with feature vectors in an unsupervised manner, and this is called k-means clustering. And has anyone heard of k-means clustering before? Okay, so a few of you. This is a very fast, scalable technique, and so it's a very useful technique to know. Google, Facebook, Twitter use this all the time to classify petabytes of data, because you can operate on data, you can look at data where you don't necessarily know what the groups are supposed to be beforehand, and start to group it into different regions. And so basically what this allows you to do is that you take an input, so some sort of feature vector representation of what you're looking at, a distance metric, so how do you define the distance between two feature vectors, and the number of groups that you want the algorithm to find, and then it comes up with a classification for each point that you give it into a group. And so if you say find 4 groups, it will give a group number for each point you put in based on this grouping. And so if we look at how does this actually look, we take this image we had before, where we have intensity, Sobel, Gaussian, and sort of these 3 different columns. We define a distance metric as sort of this Euclidean distance. We tell it we want to find 2 groups, and we end up with group 1 and group 2. And so it's sort of a division of the data. And what does it actually do? And so basically what the algorithm does is it creates sort of center points, so groups in vector space. Often this is done by randomly picking points as being a center, and then starting with that sort of initial condition. You then assign groups to data by the closest center. And so you go through each point you have in your system, and you assign the group by the closest center point to that given point. You then recalculate the centers from the mean point of each group. So this is an iterative method where you kind of have an initial guess and you update it. And then you go back to step 2 until groups stop changing, or until you reach the iteration count you're trying to go for. And so when we look at kind of what is our vector space, and so we talked about this idea of feature vectors, but this is much broader than just images, and how do we kind of define this? And so sometimes this would be physical locations, and so for example, you're trying to classify Swiss people into cities. You might use latitude and longitude as your vector space, and then your distance metric would be either sort of a scaling of this that accounts for the fact that sort of the position we are on the Earth and the distance on a sphere from one point to the other. For images, this can sort of include intensity or color. And so k-means, if you give it an intensity image, sort of provides a automatic threshold technique. So if you give it an intensity image and you say you want to find 2 groups, this will perform some sort of threshold on your image. And it's very similar to kind of what ISO data does, where you give it 2 groups and you have it iterate through until the groups stop changing. This can also include orientation, shape, or sort of in extreme cases, full spectra. So when you're doing these Raman imaging, or when you're doing sort of tensor imaging, you could put in the entire tensor as your space. One of the things to be aware of with this is if you tell it to find 5 groups, it will find 5 groups, whether or not the 5 groups actually make sense or are separable in your image. And so you have to be very careful with this technique that it doesn't usually, it will never tell you there isn't enough data for the groups. It will simply create the groups based on what it sees. Yeah?
Sorry.
Yeah.
In the example of the Swiss people classification, what would step 3 exactly do? Like kind of trying to converge, if we want to represent, for example, the citizen density.
Yeah.
Step 3 would try to converge the centers towards places where the density is higher or something.
So right. So I guess for the Swiss city one, I could take that as a very nice example. We don't talk about density there. So what we would do is basically, or at least as a starting point, you would have people.
Yeah.
So each person has a latitude and longitude. So in this room, there's a lot of people with more or less exactly the same latitude and longitude. But you could kind of have a whole map of Switzerland and 7 million little points on this map. So what you do is you would randomly take 10 people, and the hope would be is they'd be kind of evenly distributed around Switzerland. And then you would, so if we wanted to create 10 groups, you would then say, you find the closest person that I've picked in this original 10, so the closest group to where you are, and that's what group you belong to.
Okay.
And so you assign yourself to that group. You then redefine that group by the center point of all the people inside it.
Mm-hmm.
And so you would then take each one of these groups, update the center, and then go back to the beginning and reassign people groups based on what center they're closest to.
Mm-hmm. Okay.
So if you picked 10 people in this room and then tried to map all of Switzerland to it, that would be kind of a mess because your initial groupings would be horrible. But it would very quickly move away from having all 10 groups centered in this room. Because basically, if you had 4 people in this room, everyone in Graubünden would be linked to the person who was sitting there. Everyone in Wallis would be linked to the person who's sitting there. And so you'd end up with sort of the average for that, the center point for that group moving very quickly outside of this room.
Yeah. But so the centers of the group that we identified, it's very dependent on the first pick.
Yes. So it is somewhat dependent on the first pick. Often you'll have to run this algorithm a number of times to kind of get stable results.
Mm-hmm.
But yeah, it's going to be sort of linked to those initial random picks. So that you can't use this technique and say the first group it finds is Graubünden. It probably finds a group for Graubünden if you tell it to find 10. But that could be group 1, that might be group 8, that could be group 7, depending on when you ran it. But basically what you see with this technique is that it gives you the ability to kind of throw data in and get some sort of grouping out of it. And so if you have a data set that's very difficult to visualize, it makes it much easier to visualize because you now, rather than having 3 different dimensions of Gaussian, Sobel, and intensity, you can just have 2 clusters. And so it allows you to kind of incorporate n dimensions, entire spectra, and visualize them like this, and see if there is any kind of natural division in the data set you're looking at. You can also use it as an approach that once you've kind of made a k-means model, you can lock the centers in, and you can apply it to new data sets that come in. And so if you come up with a good approach for doing this, you can apply it as kind of a segmentation algorithm with those centers fixed, where you don't update the centers anymore. And so yeah, if you look for 2 groups here, you find a ring and sort of the background. If you look for 5 groups, then you find a bunch of sort of areas between them, and that's the issue you run into, that a lot of these techniques will find groups that don't necessarily make sense by looking at the images. There's probably not 5 different groups you have here, but you do see that it now has this ring as a uniquely defined group. And so keeping that and saying every time we have group 3 or 4 that's part of the ring, you would have something that fairly reliably identified rings in images like that. So in terms of k-means on real data, here's an example from I think mouse brain, where you're looking at neuron activations over a number of days. And so basically you have this time series video of an image and everything that's going on. And what you want to do is you want to classify sort of neurons into groups that fire together. The data sets on Kaggle is one of the potential projects if you're interested in. And that you can sort of, you have all these images, you have all these time points that you're interested in. You can show sort of the montage view. This isn't a great image, but sort of when it gets active, when it gets less active. And you can plot for each pixel, or for every 100 pixels here, sort of what the time curve at that point is. And so rather than looking at it as a video, you can look at it as an image, where each point in the image has an entire time series associated with it. And so here I think we just show the point number, but obviously this translates to hours. And so if you're looking at something like circadian rhythm, you want to know sort of which curves are in sync with each other, which ones have sort of a phase delay, because that probably means, this circuit could be activating another circuit, and which are doing something else entirely, and so are probably not interesting for our analysis. And so what you can do here is you can use k-means clustering, where you say look for 6 clusters. You can then run it on all the data, so it doesn't require any tuning beyond that. There's a number of parameters you can give it, but fundamentally you don't really need to worry. It's also quite a nice technique because you can parallelize it very well. And so here we run it with n jobs equals 1, so it runs as one task. But if you give this n jobs equals 1,000, you can run it in 1,000 different processes very efficiently. And so in terms of techniques that work well on 3D data that algorithms that can be parallelized are very, very good for that. And so here we can now sort of make this cluster image where we show at each point which group it got assigned to. And so this is very helpful for us because now, rather than sort of having a video that's difficult to quantify, difficult to visualize, we can see that there's these different groups. And what do you think the meaning of that group is? Or how would you derive an explanation for why pixels got grouped together? So if the input was the time series, the distance metric was just a Euclidean distance. What does it mean that these 2 points are bright blue and not purple?
It should mean that they follow similar time curves.
Exactly. So that it doesn't mean they're next to each other, it simply means the time series are similar. And so what this gives us the ability to do is really say, okay, these, they aren't all firing randomly. These appear to be firing much closer together or in much more similar ways than these groups, than these other groups. And so we didn't tell it where the pixels were when we had it run. And so the fact that it grouped them together meant there is a lot of similarity between the pixels in the same region. We can now go back and take each one of these groups, take the time series for that curve, and plot what that time series looks like for each one of the groups. And so we go through one group at a time, and we can plot sort of what the average time series looks like. And so we have this group, which sort of has this double peak there. We have this background group, which doesn't really look like anything, or, not a very periodic function. We have this one, which is also quite messy, and then we have this one, which is sort of just constantly growing. And so it allows us, at least very quickly, to say these groups are probably interesting for us. We want to focus in more detail on them. And, these other groups we can ignore because they don't seem to be following any pattern that's interesting for us. And so that's sort of why a technique like k-means is very useful, because you can take a data set where you could look at each image and say, this looks kind of interesting. You could get into some of the things we'll cover later of, where is each neuron? How do we label it? How do we track it between a whole time series of images in a reliable way? But that's a very complicated process that involves a lot of different steps. you have to be able to clearly identify what a neuron is. And I mean, by looking at these images, it's not particularly obvious. What's that? Okay, I guess that won't replay. But anyways, it's not particularly obvious what exactly those would be. And perfect. So, if you're looking here, these points are obviously fairly easy to identify as a neuron, but all of these here are sort of blurred together. And so trying to come up with individual neurons from that image wouldn't be particularly easy. And so, yeah, we can do the same thing back to this ring image where we say, include the position as well. And so now we have sort of like this connect example. I think there's a nice image for that. Is it? Oh, there it is. So that these are, in fact, real problems or real techniques that are being applied, where you have sort of some kind of cloud of points and you want to be able to classify it into body parts where the intensity itself isn't particularly useful. It's not like this is always going to be darker than this. It of course depends where your hands are. But if you include position information, you can start to say if it's on the left side of the image, it's probably a left hand or a left leg. And if it's on the right side, it's probably a right hand or a right leg. And include that to kind of come up with where the clusters might be for different regions. So we can apply the same thing to our ring image, where we include sort of the XY coordinates. And we see that we now end up with this division of the image. Does anyone have any idea why? I mean, it seems to be almost completely ignoring the image data. I mean, we did put the whole feature vector inside it, and then we end up with that output, or this output. Can anyone think of why that might be the case, or what mistake we made that caused that to happen? Yeah?
It's not a question of x coordinates. It's not because it's not the angle and the radian.
Right. So polar coordinates would have probably done a much better job because, sort of a Cartesian coordinate system, when you're trying to identify a ring, doesn't really make a lot of sense. So that's kind of the first thing. But in terms of the next part would be why is it ignoring the image information completely? Or what do we need to do to make sure that doesn't happen? No idea. Yeah? Exactly. So the problem we have here is that the coordinates for x and y are between 0 and 10. And the value from the image is between 0 and 0.4. And so when you do a Euclidean distance between, 10 and 5, that's a huge distance. And between 0.4 and 2 is a very small distance. And so, as you saw with this, to apply k-means is very simple. I mean, you go k-means clusters equals 6 dot fit, and then you put your vector in. It won't ask you, does this make sense? It won't think about your problem for you. All it will do is run its analysis. And so it's a technique that because it's so easy to use, and of course you can do it in KNIME and all of these other tools, it's implemented almost everywhere, you have to do a lot of the thinking for yourself about what actually makes sense. And so when you put in numbers between 0 and 10, and then your image data is between 0 and 0.4, 0 and -1, then of course the algorithm says, okay, on the distance metric, the changes I see in intensity, Sobel, and Gaussian are almost zero, and the changes in x and y are huge, and so when I make the groups, it will be entirely based on x and y. And so if you normalize them first, and so if you divide x by 10 and y by 10, you then end up with sort of this, obviously still using Cartesian instead of polar, so probably not the best representation of the data, but you see that it at least takes the data into account. And so that there's some sort of weighting or balance you need to do in order for it to kind of take into account all of the different factors you give to it in a reasonable way. And so when you do this, it's sort of your responsibility when you're using these tools to make sure that that makes sense. And so for the time series, it was fine because all of it was different intensity values and they were all on the same scale. But when you start to incorporate position and intensity, there isn't a clear trade-off with how many pixels is equal to 0.1 in brightness. They're completely different units. And so you have to decide what that ratio or what that trade-off is. So superpixels is kind of a further extension of this. And there we have lots of examples that take this into account. But basically it's performing this kind of k-means clustering, where instead of coming up with completely random assignments for every pixel, you focus on coming up with closed groups of pixels that belong together. And so you can take an image like this, and you don't end up with, this being group 1 and this being group 1 and this being group 1. You end up with the groups being sort of somehow physically connected, and it's much better suited for images because it can perform this on each little region of the image independently. And there you have the same idea where you have sort of this factor that links together sort of how important spatial dimensions are and how important image content is. And so this technique is called SLIC, or I think it's one of the slides we mentioned at the very beginning. And it's very useful to apply to these kinds of images. And so we have a number of examples where that's helpful, but principally what it does is it allows you to dramatically reduce the amount of data you have and focus on the individual groups. And so, for example, for doing something like segmentation, you can create the superpixels first, and then rather than having to decide for each pixel what group it belongs into, you can apply for an entire superpixel and the mean intensity what group it should be shifted to, and that then keeps the blocks sort of better together. It also is very important when we start to talk about more advanced analyses that you can do, that if you're looking for sort of objects that are vertically oriented, a pixel can't really be vertically oriented, but a superpixel can. And so you can perform sort of shape analysis and texture analysis on these groupings much better than you can of individual pixels. And so it's a significant reduction. We have it's also applicable to three-dimensional data. So we have an example there, which is part of the exercises, where you perform superpixels on CT data of people. So you can load this PET and CT image, and that you can make this sort of superpixel segmentation where you have this idea of compactness. And so a compactness very low means that it follows the image contours a lot, and a compactness very high means it just makes a perfect grid. And so here you end up with this image where it adjusts the superpixel boundaries a little bit by what you see in the image. And so where there are lungs or where there's stomach, it sort of follows that, or the boundaries of the head, but the other regions it stays straight on. Similarly with PET, you get sort of these distortions around regions that are kind of homogeneous inside. And so you can perform this in 3D. It's a little more difficult to visualize because you end up with a whole 3D segmentation of your data. But then you can apply simple rules like keep the regions that are above a certain brightness, and that you can easily then segment out an organ value rather than trying to kind of do it on a pixel basis and then having to remove a bunch of small individual pixels that got put in the wrong category. And so here you perform segmentation of these organs in a fairly reliable way. I mean, this looks quite a bit like a liver to me, and doing that with sort of a single threshold would be much harder. And yeah, when you can also weight it by the values inside it, but that's less important. But yeah, there's a whole number of tasks you can solve with superpixels. I think just yesterday on sort of another note, we were applying that to chest x-rays. So you end up with an image of like a chest x-ray. And so this is very commonly used in screening. And you can use superpixels to group this in to different regions. And so you end up with each one of these superpixels reflecting sort of a small portion of the image where that region is somewhat homogeneous. And so that allows you to kind of divide your image very quickly into a number of different regions and then keep or throw away them based on their individual characteristics. And so that's often how you see tools like k-means applied to image data. And that we so in terms of probabilistic models of segmentation, we won't get into this too much, but this is really once you move beyond kind of these fairly straightforward techniques, you get into sort of a more probabilistic view of things. And so rather than deciding concretely that a pixel belongs in class 1 or class 2, you come up with a likelihood of a pixel belonging in a certain group based on things like its intensity or its feature vector or its position, where you try to include this in sort of an appropriate manner to account for what you already know about your data sets. And so this idea with the superpixel, the idea with the k-means segmentation, was that you can assign a better group by assuming, for example, with superpixels, that regions of pixels that are close together or pixels that are close together tend to belong to the same group. So that's not always the case. There might be other problems where you'll have different kinds of models that you want to put in place, but this is sort of the general framework that you can use for framing such problems in sort of a more complicated way. Principally where this becomes very useful is where you start to do things like Markov random fields or continuous random fields, where you end up with sort of descriptions of what you expect to see in your final image and how you can incorporate things like morphology steps in a pure probabilistic model. And so where you say you don't expect to find single pixels on by themselves, and you can create a Markov random field representation of your image that includes that knowledge in order to perform the ultimate segmentation. And so that's not something we will cover in very much detail in the class, but that's sort of the approach and the starting point for getting into much more complicated problems. These techniques are becoming less and less popular because they're very difficult to set up. They're often not very transferable between different types of problems. And so if you come up with this whole probabilistic model for segmenting, this connect image, that's not necessarily usable for now classifying a X-ray or a CT scan because it's very much designed for the specific problem. And so what a lot of things have done with this area is they've moved to learning these models from the data themselves. And so that kind of goes back to the whole deep learning approach, where you take lots and lots of example data sets and you try to learn and incorporate these complex relationships by looking at lots of examples of what you were doing. So contouring, this is sort of the last thing we'll cover today, where we had the examples from last lecture with these images where sort of trying to fill all the holes was very difficult. And what we want to do is come up with a way to do that better. So how can we incorporate the information we have and this idea that we want to close all the holes in the object with our techniques. And so one of the easiest approaches here is called convex hull. And basically what this says is you find the boundary around your object that's convex in shape. And so if you take a circle of points, the convex hull of a circle is a circle. That's fairly straightforward. As you start to get more complicated shapes, what it does is it draws sort of the simplest convex region around the points that you've given it. And so when you give it these points, what it effectively does is draw sort of a triangle or a square around them that incorporates all of those points inside. The biggest problem with this technique, so it's very quick, it's computationally efficient, it's implemented in almost all of the tools that we use. So Scikit Image has it, KNIME has it, ImageJ, Fiji have tools that do this, is that it's very sensitive to single outlier points. And so, unfortunately, that's out of the field of view, but you see if you had one single point at -1, 1, your entire convex hull changes to account for that single point. And so if this is the technique you're using, you have to be aware that if there are single outliers, this technique will come up with massively incorrect sort of segmentations for what you're doing. Whereas if you did sort of a closing, it wouldn't have that huge area incorrection. So for the kind of bones examples we showed before, doing a convex hull is very useful for this because you can perform this operation quickly, and you now have an idea of sort of where's the bone, where's the marrow, what are the holes inside the bone, and that's one step that kind of gives you all that information. If you now look at just a small fraction of that image, and so if you've cut the bone into little pieces, and you then perform a convex hull, you have this massive gap because it's trying to make a convex shape around all of these points, and you have this inlet. And so for a human observer, it's clear that that doesn't belong as part of this piece of bone, but for the algorithm, because of the way it's defined, it isn't able to kind of wrap around there. And so it does a fairly reasonable job, but it still has a massive problem there, and particularly if you were trying to compare, left legs and right legs, you would end up with very different values because it's including a lot of air that isn't part of your sample. And so one of the approaches we have for this is this sort of rubber band idea where you kind of calculate the center of mass, transform the sample into polar coordinates, and then calculate sort of a piecewise linear fit. And so if you take your sample, convert it into polar coordinates, and do a piecewise linear fit around the values of theta and figure out what the values of r should be, you can do 9 points, 36 points, 90 points, 180 points, and end up with fairly accurate representations of sort of the region you're trying to look at, where it obviously has some areas here where, because the center's there and that region's there, you overestimate that a little bit, but significantly less problematic than what we had with the convex hull. You can also make sort of more flexible constraints that rather than using the maximum value, you could use sort of the mean value, or you could use a 90th percentile, which then helps you kind of minimize that problem we had before of getting too distracted by single outlier points. And so here, for example, you can account for sort of those shape differences a little bit better. There's sort of manual guided methods. So if you've used Photoshop before, Photoshop has gotten much more complicated in the recent years with very complicated image processing techniques for filling in areas and selecting objects automatically. But the older tool in Photoshop called sort of magnetic lasso allows you to sort of drag around a boundary and it finds edges that are near that. And so this is what we call kind of supervised or active learning approaches where you aren't doing something entirely automatically, but you're not doing it entirely manually either. And it's sort of a balance between the two. The principle behind many of these techniques is really to look at a group of points and focus on kind of local edge-like information, and so doing sort of edge enhancement and having sort of a bias to go towards points that are more edge-like than non-points. And this is where sort of for the brain cortex example we mentioned before, it has sort of small gradient values, but you can do that quite quickly with active contours or snakes. So there's links that go into more detail about that if you're interested. All of these techniques are also implemented in Scikit Image, so you can play around there with some of the examples that they have. So beyond, there are obviously sort of an unlimited number of techniques that are available in this area for segmentation. You should definitely focus on doing the easiest techniques first and having a clear metric for how much a more complicated technique actually delivers you. And so, if you're using an ROC curve and you go with an area under the curve of 0.8 to 0.81 by switching from a threshold to a neural network, then probably it's not worth the trade-off of using a neural network because you have a much more complicated model that can fail in much more bizarre ways, and it's not giving you a huge performance improvement. But there are obviously many cases, like those of you who tried the homework last week, where you had trying this nerve segmentation task, and trying to apply a threshold or a filter and then a threshold gives you a very poor result. And so applying neural networks can wildly improve the results that you get if you've applied them in the right way. And so clearly for that case, it's a huge added value to use more complicated techniques, but for many approaches, sort of the simplest is the best. Particularly with the more complex approaches, it's much easier to manipulate them to get the desired results. So as sort of the last example I'll show, this is from a lung segmentation example we have. And again, the neural network aspect of it isn't very important. It's the idea of sort of using a complicated segmentation approach and obviously don't worry about understanding the code or anything in particular, but basically we end up with these images of a chest, and our goal is to find the lung inside of them. And so, we have 264 images. We downsample them a lot to make it easier. We build this neural network model for doing the segmentation. They're fairly easy to build. Neural networks are much, much harder to understand and fix than they are to build. The sort of tools like Keras make it a few lines to actually make it. You have your initial model, you train it, and it actually gets fairly reliable at segmenting lung. And so you give it a picture, and it's then able to spit out this image of lung that looks fairly reliable. And so by giving it, I think, 100 examples of lung, you end up with fairly reasonable results, even though the model is not very complicated, at what you're trying to do. But if you flip the image, so if you just perform a very simple transpose, where you go from the image being this way to the image being vertical, you would expect the neural network to learn that the lung is here as well, but the network has simply memorized that pixels in this position are very likely to be lung, and pixels outside of this position are not likely to be lung. And so rather than having a method that has actually learned what lung is and how to identify it in pictures, you have a method that simply memorized these regions most of the time belong to lung and spit out those results. And so this is sort of a very clear case of if you were to do a threshold and then say, okay, everything inside the body, that's a very low absorption is probably air and probably belongs to lungs. You'd have a very robust method. If you rotated your image, if you scaled your image, you'd still get very good results. And with a neural network that's much more complicated and in theory capable of learning much, much more, you end up getting horrendous results when your data change a little bit, because this technique has a lot of very complicated parameters. I mean, if we go up here, it has 7 million different parameters it's learning from your data sets. And it's almost impossible for us to go back and understand what each one of those 7 million parameters is actually doing. And so you'll end up with a system that fails in a very, very odd way, that you would never expect that to give you the wrong result there, and yet it does. And so the idea of this is really, when you're applying these techniques, make sure that the benefit of using it is really large enough that you're justifying the fact that you're applying a much more complicated approach to something that doesn't necessarily need it. And then if you go on in this notebook, you'll see that, we can make a more complicated model that comes up with a prettier segmentation. And so by adding a second layer, we can get a much better, nicer looking segmentation out. But this one also fails in very bizarre ways. And so if we rotate the image, we now end up with something that appears to pay a little bit of attention to the image, because you end up with very weird looking lungs, but clearly looks nothing like the lungs you would expect it to find. And that you can try training it on this new data set, where you've trained it there, it now learns to do this very well. So with these models, it's always possible to train them, but if you go back to then the original images, it's forgotten what the original images are supposed to look like. And so that's kind of this very simple overview of the idea of catastrophic forgetting, that if you train it to try to solve a problem you had before, it's very likely that it will then forget how to solve the original problem, and that you can't go in and say you should really remember this and try to learn this at the same time, because the models don't always work that way. And so again, we're not going to cover exactly what the details of this are, what those weights and everything mean, but just to appreciate why complicated models can give very bad results and fail in very weird ways is sort of the point of this. And so, if you can justify what you're doing with sort of a physical model or some sort of explanation that thresholds give a really bad result, then it can make sense. With the ultrasound nerve segmentation, I think no one would argue that you can build from scratch and maybe some fancy edge filter something that perfectly segments the nerve. And so it's clear you'll need a more complicated approach, but for a lot of tasks that isn't the case, and you should then try to avoid building more complicated things than necessary. So we'll leave the fuzzy classification out, because I think that's become much less relevant now. So are there any questions on that? Or on the projects? Has everyone signed up already for